My work is called Spatial Characteristics and the Prediction of Probable Activity and Toxicity of Streptomycin and its derivatives using a PASS program. So, streptomycin is an antibiotic that is an organic base whose molecules consist of three parts: the streptidine, streptose, and the N-methylglucosamine. The next 8 models of chemical structures of streptomycin derivatives were created, and their spatial characteristics were calculated using a Gaussian program. We can see them there. Is the first 4 and the next 4. They have a different functional group, which is the reason of the differences in their pharmacological and toxic properties. Using quantum chemical studies, analysis of calculated enthalpies of the formation of these model molecules shows that all of the models are most thermodynamically stable. And next, we calculated the HOMO and the LUMO energy, which is the highest occupied molecular orbital and the lowest unoccupied molecular orbital, and the differences in their values. This shows that these compounds have a high stability. Next, the analysis of charge characteristics on atoms in a model molecule shows that the reaction center for nucleophilic attack is oxygen in a single bond in a hydroxyl group of streptomycin derivatives, and the nitrogen with a double bond in the guanidine group. Next, we calculated dipole moments of this model and compared them with polar solvents. This shows that most of the compounds, except for the number 3 and the number 7, are soluble in the most polar solvents, which means that these streptomycin models can be applied injectively in theory. Next, using the PASS online program, pharmacological and the toxic effects for these 8 models of streptomycin derivatives were calculated, and not only their pharmacological effect, but also toxicity values. And there is some patterns that I would like to share with you that analysis show there's a presence of phosphoric acid residue in the structure of streptomycin number 2. Increases antifungal effect and decreases the toxicity scores, which is mutagenicity, reproductive dysfunction, and carcinogenicity. The next, absence of guanidine group and the presence of phosphoric acid residue in the structure of streptomycin number 3 is significantly increases the probability of having antifungal and antibacterial effects, and it decreases the toxicity in overall. Next, absence of a guanidine group in the structure of streptomycin number 3 significantly increases the probability of having antitubercle activity compared to other models, and increases the toxicity indicators of the compound. And the absence of a guanidine group in the structure of streptomycin number 5 and the replacement of an H2 group by OH group significantly increases the antitubercle activity compared to other models of the streptomycin, and reduces the toxicity indicators, mutagenicity, reproductive dysfunction, carcinogenicity, and visual toxicity. The next, there are some patterns that I would like to share with you. Is that the streptomycin models have strong antifungal activity, and the compounds number 1, 4, and 5 shows this activity, and this activity increases with the charge unit of charge and the dipole moment values. And the next one is antituberculosis activity. So streptomycin, all of these models of the streptomycin shows antituberculosis activity, and the most stronger is the number 2, number 4, and number 5. And there's also this pattern that activity increases with the charge and the dipole moment values. So streptomycin is an important antibiotic in modern medicine, and the search for its derivatives is a current pharmaceutical problems. We believe that the result of this work will be useful in the development and research of new drugs, and will reduce burden on the laboratories and research centers. So this is all. Thank you.
Thank you very much for your talk. There is some questions to you. For example, one question from Professor Solimov: how do you calculate dipole moment?
We actually didn't calculate the dipole moment. We just used the Gaussian program, and it gives us these dipole moments, and we just compared them with most used polar solvents in nowadays medicine.
Another question from Vladimir Paroikov. Do you think that probability of activity estimated by PAS represents the potency of the particular activity? There is coincidence with activity and prediction, in other words.
Can you please repeat all of this? Okay. This PAS modeling, PAS program shows probable activity, and of course, if we are going to synthesize the streptomycin new derivatives, and these models will be useful, so we can trust them because the PAS program uses a huge database that can show a probable activity, but of course, it is not the actual activity. If we're going to synthesize these molecules, these models, these antibiotics, we are going to do actual testings in a laboratory, but these models give us information that we can use in a synthesis. For example, by comparing the dipole moments of the compound number 3 and the number 7, we understood that these models can't be solved in a polar solvent, so they can be used injectively in the medicine, but a lot of the antibiotics use it injectively. So we can assume that number 3 and the number 7 models are not sufficient to synthesize this in a laboratory. But if we are going to do synthesizes, and we will do actual tests in laboratories.
Another question is from Dmitry Shulga. Calculated dipole moments are highly dependent on the geometry used. For the compounds you study, multiple conformations are possible. How would you comment on the selection of the conformers to estimate dipole moments and other calculated properties for single molecules?
We didn't only calculate the dipole moments, we also calculated highest occupied molecular orbitals and the lowest occupied molecular orbitals, and we choose the most optimal configuration of these molecules, and we choose the most estimate ones.
Question from Professor Sulimov. How do you calculate charge?
The unit of charge, I guess, right? So
yes. You told that you calculate dipole moments with Gaussian. So how do you calculate charge of the molecules? Protonation. Did you make how do you use protonation states or in solvent? How to analyze it?
So again, I'm going to tell this again. We just used it Gaussian program to calculate the unit of charges. The program give it as this unit, and on these units we just assume it that that which centers is going to be the centers of the electrophilic attack, and which centers is going to be center of a nucleophilic attacks.
Thank you.
Another question from Roman Yefremov. How useful for conclusions with the data derived from quantum chemical calculations? It's my question too. How useful for the conclusion?
For the conclusion,
was this data what you found from quantum chemical calculations?
So streptomycin is actually second opened antibiotic in the world after penicillin, and it's widely used now. It's used in the treatment of tuberculosis, for example. And nowadays there is a really serious problem of antibiotic resistance. And since streptomycin is a really old antibiotic, there's a lot of people with resistance to this. And opening new derivatives of this is a real problem in nowadays medicine. And these calculations will help to have a oriental unit, the oriental oriental numbers for the next synthesis. So it helps us just to understand which model is the most sufficient to synthesis, because a synthesis in a laboratory takes a lot of time, a lot of money, and so on. And on this
Thank you.